since we're talking about extended objects, now let's summarize the key properties that extended objects have. Okay, so I'll split that. I'll classify that into intrinsic properties, and then extrinsic ones. But I'll also split them into kinematics properties and dynamic properties. So kinematics, how things move, and dynamics, in some sense, why things move. So this is independent of forces. This is depending on forces. Okay, the forces on the object, right? So before, with linear motion, objects only have mass. Okay, but now we have for extended objects, we need to worry about the center of mass, and we will learn how to find the center of mass with an irregular object. Okay, and then there's another concept, right? So mass, in some sense. Right, the mass in some sense, what was the definition of mass? Is a measure of its inertia. So it's what's inertia is a resistance to motion. So mass is a measure of its resistance to motion. Okay, a measure of the objects, by its I mean the objects, resistance to motion. Okay, it's a way to measure it. And how do we measure it? It's by applying a force and see how fast it accelerates. So that's basically how you measure mass. So this is what we call inertia. Now, we realize that when it's extended, when you apply a force, if you apply it to the center of mass, it will create linear motion. Okay. Now, if you don't apply it to the center of mass and you apply it somewhere else, what you will do is you will cause it to rotate. And however, some things will rotate easier than the other. And the key thing that changes how easy it is to rotate instead of how easy it is to move linearly is its shape. Okay, and we have a quantity, so we should come up with a quantity to measure. So we need a measure or a measurement of the objects. It means the objects resistance to not linear motion but rotational motion. Okay, or rotations. So this is a new type of inertia, right? This is in some sense linear inertia, and this is rotational inertia. Okay, so resistance to rotational motion, you can call it rotational inertia. Okay, so this is how mass is center of mass is the location of where the mass, it's the location where when you push that, it will go in a straight line. Okay, and mass, so technically center of mass is the location where the object will move linearly when a force is applied on it. Okay, so that's the center of mass. We'll write down the formula for that later on. But here, when I was writing this, I'm defining mass. Okay. Now, mass is a measure of something's linear inertia, and so that's how much it wants to resist linear motion. And we need a new concept to tell me how much it resists rotation. Okay, it's not necessarily the same thing, and it depends on the shape, right? The same mass object with different shape and the same center of mass, but different shape can rotate differently, right? So if imagine all the mass is concentrated like a marble in the center, then would that be, you can give that a think, would that be easier to rotate than if the mass is spread out like a long pole, right? A long pole, would it be easier to rotate that or rotate all the mass concentrated near the center of mass? Okay, and it comes with a name, and that's one of the most confusing name of all, and it's called a moment of inertia. Okay, so right off the bat, so these are the two next things we will talk about. Right off the bat, I will need to tell you, so this is usually given the symbol I, do not call this inertia. Every 10 times I might have one or two times I'll have a slip of tongue and I might call that inertia. But try your best to avoid calling this inertia. This is moment of inertia. It's an annoying name. It doesn't have a better name, unfortunately. Someone should come up with a better name. If you have any suggestions, let me know below. Yeah, it's moment of inertia is not inertia. Okay, when you say inertia, the connotation is linear inertia, is how much you resist linear motion. Moment of inertia is what mass is for rotations. Okay, it's how much it doesn't like to rotate. Okay, so I don't know a better way of saying this other than be careful. Say moment of inertia. It's different from inertia. Don't say inertia. Okay, but there will be 10% of times maybe we are so lazy that we slip the tongue and say that. But yeah, we'll see that in a little bit more detail. Is just like m is how much force resists accelerations. Moment of inertia is how much a rotational force, which we call torque, which is curly t, which is the Greek letter of tau, over angular acceleration. So you change, this is the rotational version of force, and this is the rotational version of acceleration. And we'll see that in more detail, okay? So as you know, extended objects, now we suddenly care about rotation. So what are the kinematics property other than the its linear motion? Is its rotational motion or angular motion? Okay, so the kinematics property is its position. If it's one dimension, it's x. If it's 3 dimension, it's r. Right, both the 1D version and yeah, let's do that 1D and 2 or 3D version. The position, the displacement, the velocity, acceleration. The initial velocity is also velocity. So s is change in position, right? And time is just a universal sort of ticking clock. That's not really a kinematic variable, it's a kinematic parameter. We've talked about that, but small difference, don't worry about that, right? So really the key thing is x of t, v of t, and a of t, right? So it's where it is, right? And in 3D is r of t, v of t, you can have delta, you can have delta r, that's displacement. So, right, that's the position it is at minus its initial position. So that's position, displacement. So just to keep this concise, we'll write that. Velocity and acceleration. Right? And really just to keep things concise, maybe I won't write displacement because that's just a change in position. Right, so I'll just adapt a formal approach and have sort of these key variables. And rotations has to say, when things are rotating, now we have an angular version of everything over here. So instead of talking about where it is away from the origin, we talk about how much angle it is away from the initial angle, and that's theta. Okay, so theta of t. So if things rotate, usually we treat it as a polar angle, and we're talking about rotations on a plane. Again, not the flying machine that goes in the air, but just a two-dimensional surface. It's a plane. So any rotation, the minimum dimension you need is 2D, right? We will not talk about rotations in 3D, which is much more complicated. So we'll focus on the easy parts, right? We'll let the engineers do the more difficult part, and the proper physicists will deal with that. For now, let's start off easy, right? So just the angle and how, so V is how fast does X change. So we have omega, that's how fast theta change, d theta dt, same sense, right? And the angular acceleration alpha of t, and that's how fast the angular speed change. This is how fast the linear speed change, like that. Okay, so these are the kinematic variables, and dynamically there are two main things we talk about. For linear, we talk about force, right, in 1D or in 3D, but we ultimately talk about force. And this is the linear dynamics. And for rotational or angular dynamics, we'll talk about torque. Okay, so this is called torque. But what you will understand this as, all you need to do is think of this as the rotational force. Okay, so this is the force that causes, this is the force that causes rotation, essentially. Okay, and we also have momentum. all right, or in higher dimension P, and we have angular momentum. Okay, so it's usually called L. Okay, so this is called, I don't need a bracket. This is called angular momentum. So you could call this angular force. It will make more sense, right? Force, angular force, momentum, angular momentum. And if you want to emphasize, call it linear momentum. If you want to emphasize the difference, okay? So these are the key players of our subject, and we'll start with looking at this, and then move our way through through this table.